Shuts down as prices fluctuate with the shafts.
Yeah.
Yep, we're ready.
Very good. Okay, I just introduced you shortly and then.
Yep.
we can start. Good afternoon, everybody. Sorry for this intermezzo, but yeah, technology sometimes just outcompetes us from here. So I'm really happy to welcome here Loren, Burmeister, and Mike Borduin to our restoration seminar. I'm really delighted they accepted our invitation because it's great topics and important issues that we'll be talking about. And it's great to have somebody from ARCO and from Pioneer.
Pioneer, yes.
Yes. So before they start their talk, I would like to introduce them shortly. Loren Burmeister obtained his engineering degree from the MSU Bozeman and began working the Butte and Anaconda Superfund sites in 2009. Loren currently functions as a BPSOU, that's the Butte Priority Soils Operable Unit project manager for Atlantic Richfield and BP, and lives in Butte with his wife and children. Mike Borduin, do I pronounce your name correctly?
Borduin.
Borduin.
It was close.
Obtained his master's degree in hydrogeological engineering from Montana Tech and began working on the Butte and Anaconda Superfund sites in 1999, specializing in groundwater capture and treatment. So with this, I would like to welcome you again and looking forward to your talk. Is that dark enough? Should we close? Okay. Just a second.
Okay, so we
roll those hat down. And then
and roll these ones down?
yeah.
Roll these ones down. Oh, that's good. That's good.
Wish I had those in my house.
Yeah.
First, the kids would be playing.
Yeah.
It can go all the way down.
That's right.
So thanks again. And
All right. Well, thank you, Robert. I'm Loren Burmeister, and this is Mike Borduin. So we are here today to talk about Butte Priority Soils, or BPSOU groundwater, and the remedy that's been implemented here in Butte. So just as a little bit of history, what's shown up here on the screen is the NPL site, which was listed. Silverbow Creek NPL site was listed by EPA in 1983 on the national priorities list and expanded in 1987 to include the Butte area. So you can see down here at Missoula, 120 miles up all the way to here in Butte. So the focus for today is around the Butte area. You can see here the Butte boundary in red, the Butte mine flooding boundary in black. So these sites actually overlay each other a little bit in that the Butte mine flooding operable unit extends under Butte priority soils in the bedrock groundwater. So today we'll be talking more about alluvial groundwater. So again, you can see here the Butte priority soils operable unit encompasses the upper part of the Butte Hill. It's about 5 square miles with Blacktail Creek and Silverbow Creek bisecting the site and then extending down to the Copper Mountain Sports Complex. So a little more brief background on this. There's 3 primary areas of concern for the BPSOU that are identified in the record of decision. The first being solid media. So all these shaded areas you see up here are actually historic mine waste sites. Mine waste dumps that have been reclaimed through critical time removals by EPA starting, or by Atlantic Richfield at EPA's direction starting in 1987. And these source areas were basically why the boundary was designated where it is, why it's priority soils. So in addition to solid media, another area of concern is stormwater on the Butte Hill. So you can see it's a very complex network of municipal stormwater sewers that transverse the site, and then the shading indicates different sub-drainages. So we also address stormwater on the Butte Hill. And finally, the remaining area of concern and what we're here to talk about today is the groundwater in Butte, and primarily in the area of the corridor here and down along Blacktail here. With that, I'll turn it over to Mike.
We need to switch microphones. Okay. All right. So we're talking about groundwater remedy, right? And so I just wanted to emphasize what remedy implies. And that's basically protection of human health and it's protection of the environment. So before we get into groundwater remedy and what's been done in the way of capturing and treating groundwater, we wanted to go over a little bit about what has historically happened in the area and just to give a context of what we're dealing with here. So I'm assuming most people in this room are familiar with the main tailings impoundments and fluvially dispersed tailings along Upper Silverbow Creek. You've got Parrot tailings here. Just a little orientation. There's Blacktail Creek, Silverbow Creek, Upper Silverbow Creek, with a Berkeley pit behind. You've got Northside tailings and diggings east. So, these were put down over 100 years of mining impact, starting in the 1880s and progressing through today, essentially. So, mining actually began in 1864, and so you have that long history of mining impact. So stepping back to about 1955, this is kind of what the Upper Silverbow Creek Basin looked like. Again, here is Parrot tailings and diggings east down here. You'll notice the Berkeley pit isn't there yet. Silverbow Creek was still flowing up into this drainage. From this drainage, there were, in addition to the Parrot smelter, there were 3 other smelters that were contributing tailings to Upper Silverbow Creek. These operated for about 18 years in the late 1800s and put about 100 tons of tailings per day into Upper Silverbow Creek. So what else was going on at this time? Something that you can't really see by looking around is that down Upper Silverbow Creek channel, process water was discharged and mine dewatering and pretty much anything liquid, tailing slurries. For example, in 1972, this channel was flowing at 29 CFS, entirely mine, process water, discharge water, etc. That's 3 times what base flow is in Blacktail Creek. It's a tremendous amount of water. So you have these tailings impoundments, you have this large flow of water. All of that water is percolating down to groundwater. And this isn't pristine water either. It's pH 2 to 3, laden with copper and cadmium and zinc. So as that water flows down, a portion of that is flowing out into the aquifer. So this is kind of what it looked like in the day. You've got Parrot smelter in the background, I believe, with tailings in the foreground and Silverbow Creek here. So if you were to slice into the earth, roughly along the channel, what would you see? So you've got Parrot tailings here, Here's Upper Silverbow Creek Channel, north side tailings, diggings east. What happened to all that water that was lost out of that channel, out of those ponds? That percolated down to groundwater and proceeded to flow through groundwater. The metals were left behind. So you have a large, what we call a dispersed source that was put into place over 100 years. Keep in mind this impoundment was working for about 18 years. This source was put into place over a duration that was 5 times longer. So given that, the largest remaining source of metals in this drainage, this Upper Silverbow Creek drainage, is the aquifer itself. This goes down quite deeply, as anywhere from 40 to 70 feet in depth, and would be very difficult to remove. All right, so how do we know this? How do we know about the dispersed source and the impacts to the aquifer? It really started with the RI, the Remedial Investigation and Feasibility Study in 2004. And that was kind of the first time that scientists and engineers were able to really dig into this area and figure out what was going on. Using the knowledge that they had, that became a technical impracticability waiver, which was granted in the ROD in 2006. And basically, that TI waiver said that groundwater quality cannot be restored to pre-mining conditions. So that basically sets the stage for what has to be done in the area. Now, they didn't have all the information that we have today, but several other investigations since then have supported this general finding. In 2009, there was a tracer study in the subdrain itself. The most notably was a pumping test in 2010 that was co-performed between Atlantic Richfield and the Bureau, actually. And that's when we found out that the hydraulics in the aquifer were a little bit different. Several other groundwater studies, all kind of culminating into the MSD Groundwater Management Report in 2015, that generally support that, yes, the aquifer is the largest remaining source of metals in the aquifer. So what does that mean? EPA has now recognized, okay, we can't clean up the aquifer, but we do need to, under remedy, be protective of human health and the environment. And so in the ROD, basically the finding is that because groundwater in this area can't be cleaned up, that the most effective means of protecting the surface water, that is the environment, is capture and treatment of impacted groundwater. So that's what we're talking about today, is that capture and treatment, how it works, and the current means and methods that are used to look at how effective that system is. All right, so the TI zone, where is it? So here's Upper Silverbow Creek, Blacktail Creek, and then here's the edge of the site, the Butte Priority Soil site, right at the interstate there. The TI zone is essentially what's shown in purple. This was the portion of the aquifer that EPA recognized as not restorable. So that in itself doesn't really protect human health and the environment. It just says that you can't restore it. To protect human health, i.e. drinking water from wells, a controlled groundwater area had to be put into place. And that's a little larger. It's this kind of tannish boundary here, which basically says that groundwater wells cannot be drilled in this area. So that protects the human health side. All right, so as we go back to this slide, we'd start looking at how the groundwater capture system works. Now that you kind of understand the dynamics and where the impacted groundwater is coming from, we'll take a look at what was put in place in 2004. So essentially, the groundwater capture system, if you picture a groundwater capture well, and turn it on its side and extend it to be about a mile long, that's essentially what's in place underneath the upper Silverbow Creek channel. So from right across the street from the visitor center all the way to the Civic Center, right at the train there, is where the subdrain is. So if you look at it, if you took a slice right there and looked at the side view, you would essentially see this. You've got the channel, which you can see, and the objective of the subdrain is to separate the underlying groundwater from the intermittent surface water that flows down that channel. Today it's mostly stormwater. So to separate those two, you have a clay liner that is more or less impermeable, and then you have underneath it the groundwater capture system. That system is essentially two components. You've got a larger gravel pack around it. It's about 4 feet by 4 feet. And inside that gravel pack is a 10-inch pipe. And that pipe is perforated to let groundwater go into it. So on average, about 560 gallons a minute flow into this pipe and are treated. So essentially what happens is this, because we're removing groundwater out of this area, draws the water table down, and in turn makes this the lowest potential area to the adjacent areas. And so the adjacent areas, groundwater from those areas, also flow basically from areas of high potential to areas of low potential. Groundwater flows downhill in a water table system. So that's the general functioning of the subdrain. Now it's going to get a little more complicated here. So as you step out away from the subdrain, as I mentioned, we're changing the groundwater surface. We're creating a groundwater depression, much like a pumping well would. You essentially change how groundwater behaves through the area. So here's our subdrain. We've depressed groundwater, and now it's easier for groundwater to flow this way than it is to continue along the previous route before 2004. So essentially, along the shallowest portion of the aquifer, your capture extends approximately to the edges of the blue polygon. You can see Blacktail Creek to the south. Capture zone doesn't extend to the creek. And then here's the confluence of Upper Silverbow Creek and Blacktail Creek. All right, so what about vertical capture? I've got a pipe, it's 5 feet down in the ground. How is it going to ever capture impacted groundwater that's 70 feet deep? And the answer is that the design takes care, or took into consideration, natural conditions, and use that to optimize the design. So if you were to take a slice in the earth here, like so, you would get basically this cross section here, where back at the Parrot tailings you would have about more than 200 feet of alluvium. But as you work your way to the west, down to Montana Street, that thickness drops down, to about 20 to 30 feet. So as groundwater comes down the valley, there's a lot of groundwater over here pushing downwards like this. This bedrock surface is coming up. It's more or less impermeable, so a little bit groundwater can flow through it, but by far the majority stays in the alluvium. So as it comes down and is pushed into a smaller and smaller area, the easiest way for that groundwater to flow is basically up. And you can actually see that with your naked eye right here. There are wetlands here to the south of the interstate and to the south of the visitor center. There's some more along the walking trail. Those are all from groundwater upwelling to the surface. It's basically the same concept of what makes an artesian well, right? There's that well on the way to Discovery ski area across from the Job Corps that flows and makes a huge stalagtite in the winter. That groundwater flows out of the ground. So because there were these conditions in this area, that's why the subdrain was able to take advantage of those conditions. So how far down do we capture? And basically we have in green as a dispersed source in the aquifer. Essentially our capture zone is approximated to extend down roughly to the same depth of the dispersed source. So I'll get into a little bit more on how we do that later. All right, so we're going to put this picture, the horizontal extent, together with the vertical extent of groundwater capture, and essentially you get a boat of extent of capture, which is this purple polygon here. Again, you have paired tailings with Upper Silverbow Creek. You have your dispersed source. Notice that most of this dispersed source lies within the three-dimensional capture zone from this system. All right, so that kind of summarizes the subdrain in the Upper Silverbow Creek area. Let's move down a little bit to lower area 1. Here's Centennial here and the Metro Sewer Plant, Silverbow Creek on the interstate. This is also a groundwater capture system. It's combined, there's a lot of ponds here. Some of them work to capture groundwater. Some of them, as Loren's going to talk about, treat groundwater. So this is the extent of what we call the Butte treatment lagoons, is this polygon here. So essentially you have ponds and ditches that are built much like the subdrain are. They're depressed into the groundwater table, and because they're pumped or they flow under gravity, they draw groundwater from the surrounding area into them. So you've got BRW capture pond here at the far east end, which captures groundwater from the old Butte Reduction Works area. You've got this very long hydraulic control channel that extends the length of the site. And then, so groundwater from the north, from the Butte Hill, is captured in these features. In addition, you have losses from these treatment cells that also report to the HCC. And finally, you have the D4 cell. This is really what makes the whole thing tick. This cell has been depressed quite a bit more than the HCC, and is in fact the lowest surface water in the valley. It's the lowest groundwater in the valley. So that controls the groundwater coming out of Summit Valley. In addition, when the Butte treatment lagoons were made, the creek was also reconstructed. And it was constructed in such a way that the creek was higher in elevation than the groundwater treatment system. So any impacted groundwater from this treatment system, if it escapes, would be lower in elevation than the creek, and any losses from the creek would be captured by the treatment system, like so. So to give you a little better idea of how that works, I'll take a slice across the D4 cell here. And essentially what you have is a D4 cell in the middle. You can see how much more notably lower it is than either the hydraulic control channel or Silverbow Creek. So any losses here from on the north side of the creek report to D4, and likewise with the hydraulic control channel. So the other, I talked about how the upper Silverbow Creek subdrain was optimized. This system was also optimized where the depth of bedrock is only about 6 feet below that D4 cell. So there's not very little groundwater flowing through this bedrock. So that's kind of a summary of how groundwater is captured and why it needs to be captured. Now I'm going to hand it over to Loren again to talk about groundwater treatment.
All right, so just to recap at a high level, Mike talked about the subdrain system, and then as you work down the site, you get down to the Butte treatment lagoons where you have additional capture and treatment with Silverbow Creek running down below the site. So from those systems, those captured impacted waters are coming into our treatment system. So from the subdrain, it's pumped from right at the visitor center over to here at about 400 to 600 gallons per minute. In addition, you've got the West Camp pump station, which sits right along Centennial Street, where we pump out water from the mine workings of West Camp at about 100 to 200 gallons per minute. And then we have a Missoula Gulch base flow component that's coming down the stormwater channels that we capture and treat that makes up another 100 to 200 gallons per minute. So you've got about 200 to 400 GPM coming in from there. In addition, the BRW capture lagoons at about 200 GPM, and then the HCC flowing along here at about 200 GPM. So all of this water eventually culminates down in D4. And D4 is depressed, as Mike mentioned, and sits atop the highest bedrock. And so that's ultimately our final capture point. The highest bedrock, lowest groundwater depression, the best area for capture. So from that point, our treatment system begins. So we've got a pump station here that pumps water up to the head of our treatment system, averaging between 1,000 and 1,800 gallons per minute. So that water is pumped up to our operations building and to a chemical addition system. You can see here in tan, this is a silo that contains hydrated lime. So in order to start the treatment process, we add lime to the impacted water to basically raise the pH level and start the precipitation process. So the water that's coming in at this point is typically a fairly neutral state of 7 to 7.5 pH. Then we add lime in a slurry tank at about 110 milligrams per liter, or what would be equivalent to about 1/16 of a teaspoon per gallon, to raise the pH up to 10.5. So it takes very little lime to actually raise that pH up. And the reason we need to raise the pH is that starts the precipitation process. It starts to force those metals out of solution. So the most difficult is probably cadmium, and that's the reason we've got to go all the way up to 10.5 to start that process. Just to give you a little bit of reference, in 2016, we treated over 600 million gallons of water through this system and used over 290 tons of lime to treat that water. And our flows averaged anywhere from 730 to 1,650 gallons per minute. So once the water has worked its way through the chemical additions building, that water is split in a mixing tank between 3 different lagoon series. starting with the 1 cells, A1, B1, and C1. The water has just been treated with lime and comes into these cells. And the reason we designed them this way, you can actually see the light little lines right there, right there, right there. Those are silk curtains, and by concentrating the most recently treated water up in those front cells, we're able to perform easier maintenance. So you can see how these are a little more green than the remaining cells. In those first cells, the lime is already starting to precipitate out, and those silk curtains further assist in that, so that all of our solid flocculant, or the majority of the solid flocculant, is actually captured in those 1 cells. And that allows us to go in with the dredge twice a year, dredge out those solids, allow them to dry, and then we take them up to a repository for disposal. So as the water works its way down from these are the A cells, the B cells, and the C cells, and the 1, 2, and 3. It works from right to left, from the 1 cells to the 2 to the 3, over about a 7-day period. And this 7 days allows the water to start to come back towards a neutral pH. It also allows those metals to continue to precipitate out. So by the time you get to the end of A3, after about a 7-day period, the water has come back down to an average pH of about 9.2. At that point, it's ran through an automated sampler so that we can measure the metals loads, the pH levels, to ensure we're in compliance, and then it's discharged to Silverbow Creek. The water flowing out of our treatment system is coming out at about 2.5 CFS, or around 1,000 GPM. So just as reference, Silverbow Creek beside it is running at about 10 CFS. So the flows coming out of the Butte treatment lagoons is about 1/4 of the flow going down the stream under base flow conditions. So how do we know the system's working? Looking at copper as a reference, you can see here in green, these are our concentrations of the influent water coming into the system, with the 1 representing 1,000 parts per billion, roughly, is where our influent flows are, to the maroon, which is about 10 parts per billion on average. And then you can see the standard here. So the standard at a max hardness of 400, which is what we have because of the lime system, the lime addition. The standard here is at about 30 parts per billion for copper. And zinc and cadmium would have similar charts. Oop. Oh. I'll turn it back over to Mike.
All right, thank you. So one last thing on this slide before I move on. This influent and effluent concentrations over that average flow is about 5.5 pounds of copper that's dropped out every day in this system. So we've talked about why we need groundwater capture and treatment. We've talked about how groundwater is captured, how it's treated. Now we're going to get a little bit into how you measure the effectiveness of the system. Obviously you can build anything you want, but the proof is in the pudding. And in this case, the proof is really in the creek. Getting back to the purpose of the remedy, it's to protect human health and the environment. Human health is protected through the ban on water wells in this area. It's a little trickier to show that you're protecting the creek. And basically what is required there is that you meet state groundwater standards. We're going to be looking at standards at SS7, which is right where the interstate crosses Silverbow Creek basically at the edge, the down gradient site, downstream site in Butte priority soils. So there's really 3 different measures of looking at how the system is working and making sure that it's effective. The first system is a system within the groundwater aquifer itself. It's a bit of a sentinel system or early warning system. The second level is really looking at what you're capturing in your capture system. The flows are monitored in real time, the chemistry is measured, and just ensuring that your capture continues to be effective. And then finally, you have the data in the creek, which the USGS measures, and we'll get into that. So the first level of effectiveness, as I mentioned, is groundwater. So throughout the site, from one end to the other within the alluvial aquifer, there are many monitoring wells at different depths. Every month, these wells are measured for groundwater elevation, the depth to groundwater, and twice a year, 119 of those wells are sampled for chemistry. So that's nice. What do you do with that data? The groundwater levels, as I mentioned before, really ensure that that groundwater capture system is operating at the proper elevation. The chemistry is really an early warning system if conditions are changing. Say more impacted groundwater is starting to change flow direction. So basically what is done is that those wells are looked at depth-wise and also over time. So the aquifer underneath Upper Silverbow Creek is actually very deep. There's 3 different units in it. There's the upper, which is this upper strip here. There's a middle depth, which is between 40 and 50 feet, roughly. And then there's a lower portion, a lower unit, between 60 and 80 feet. So as you can see, these symbols, triangles and circles, are all monitoring wells that are completed in each one of these units. And they are color-coded based on their concentration, but they're also evaluated over time to see are concentrations of metals increasing at those locations or decreasing. So these are sampled on average, well, they are sampled every 6 months. So that serves as an early warning system for any groundwater that might be flowing towards the creek. So that's kind of the first measure of effectiveness. The second, as I mentioned, was the capture within the subdrain. So real-time monitoring of flow. This chemistry is also measured twice a year. As I mentioned before, it's 560 or 70 gallons per minute on average that's captured in that subdrain. If you take that load and the load within the creek, essentially that makes up 100% of the load coming down into the aquifer there. Essentially, if you treat that load as $1, as 100%, the subdrain is capturing 97% of that copper, cadmium, and zinc that is coming down Upper Silverbow Creek, or 97 pennies out of the $1, with the 3 pennies remaining in Silverbow Creek. So essentially what this is showing is that the subdrain captures at least 97% of the load and is therefore about 97% effective at removing these metals. So that brings up the question, how about these 3 pennies? What does that look like in Silverbow Creek? Shouldn't we be capturing these 3 pennies? So that's where the final measure of effectiveness comes in, the actual measurement in the creek itself. And we'll go to that next. So this is data from the USGS has collected over quite a long period of time. It started in January of 93. And they collect down, I mentioned station SS7, right there where the interstate crosses the creek. And as you can see, in the early days, copper was up there. This is the state water quality standard down here, or nowhere near compliance. This is total recoverable, by the way, and it is hardness adjusted. The more hardness, the lower the standard, or excuse me, the higher the standard, and vice versa. So over time, I'll just step you through the different upgrades and additions to the groundwater capture system and what that did to our groundwater quality. So kind of the biggest bang for the buck was really the construction of LAL from 98 to 2001. You can see copper in this range, 100 to 450 and higher, now drops to below 150 on average. Now this is base flow conditions. This is not stormwater. So that made the first major improvement in water quality in Silverbow Creek. Then the subdrain in Upper Silverbow Creek was constructed between 2003 and the fall of 2005. There's a little bit of optimization and shakedown here, but if you can see this, most of these points are above the standard. Now we're finally starting to get down below the standard. But we're not done yet. 2010, 2011, right where Blacktail Creek and Silverbow Creek come together, there was a remediation effort there. Around the Butte reduction works, there was some impacted groundwater coming into the creek. That source was removed, and so on and so forth. And you can see we're really getting towards where you kind of have to squint there to see whether you're above or below the line. So, but in general, you've got a very strong downward trend suggesting that are we capturing impacted groundwater? I think this supports that we are. All right, so let's zoom in on this little box here. Again, we have our standard, hardness adjusted standard. That's why it's moving around. Subdrain constructed here, other optimizations here, so that by the time we're done in 2012, most of these copper concentrations are falling below the standard. And then finally in 2006, the creek actually meets total recoverable copper concentrations 100% of the time. So it's really, really, if you step back to 1998 and realize the creek met the copper standard 0% of the time, that is 100% of the samples did not meet standards, and now in 2016 it meets standards 100% of the time. So quite a turnaround. All right.
So as we've shown here today, the capture and treatment system that was selected and has been installed for the Butte priority soils, Atlantic Richfield agrees is the proper system for ensuring that human health and the environment are protected from groundwater. In addition, as Mike was talking about the sentinel wells and the evaluations of the groundwater, surface water, and the system, we also are confident that the program we have in place is adequate to ensure that if conditions change, we can appropriately react to those changes and remedy the situation. And finally, we are committed to seeing this thing through. The environmental remedy work that's left to be done in Butte will be done to ensure long-term protectiveness of human health and the environment. So with that, if any